We dealt with them in terms of integer value exponents, so it was nothing too crazy. What we're looking at now today is we're taking this a step further. We're looking at going into rational exponents. So the properties of all that we've looked at before, all those same properties hold true. None of those have changed, but what we're going to do is just start working with fractions. So that means you have to know how to add, subtract, multiply with fractions. Don't freak out, your calculator knows how to do that. Okay? Remember, the alpha y equals button will allow you to put in the numerator denominator real quick, or if you want to write it out in terms of parentheses, you can do that as well. So what I want to do here is just kind of walk you through a couple of the examples, just to remind you guys of how this stuff works. When you have the same base with different exponents and you're multiplying them together, all you have to do is add your exponents. In this example here, it's 3 to the half times 3 to the 3 halves, which means all I have to do is add my exponents. How do I add my exponents? Yep. What's 1 half plus 3 halves? 4 halves. So this becomes 3 to the 4 halves, otherwise known as 3 squared, which is 9. Okay? When you have power to power, that means you multiply your exponents. So you have 3 halves times 2. 6 halves, otherwise known as
3.
4 cubed.
4 cubed.
Otherwise known as
64.
64.
Yeah.
Okay. Again, you're using the same properties as we've done in the past, but we're just working with fractions. Okay? When you have a bunch of junk raised to an exponent, remember in this case, since it's multiplication, it's like distributing the power. So you wind up with 9 times 4, all to the half power, which is 9 to the half power, 4 to the half power. And what does half power mean again?
Squared.
Square root.
Square root.
What's the square root of 9?
3.
Square root of 2. 2 times 3 is?
Square root of 2 is not 2.
Square root of 2 is not
I said square root of 4, excuse me.
There you go.
It's funny, last hour I said the square root of 3 is 9. I basically did the same thing the wrong way twice now.
Isn't it 5? Because 3 plus 2 is 5.
It's multiplying.
Oh.
If it was plus, yes, you'd be right. Again, it's a negative exponent. Are negative exponents happy in the numerator?
No, they're
Where are they happy?
The denominator.
So this becomes 1 over. And what's the half power of 25?
5.
Again, in this case, you have division. You have the same base, different exponents. You play the game of war. Who wins? 5 halves or 1 half?
5 halves.
What's 5 halves minus 1 half?
4.
4 halves.
Otherwise known as 2.
2.
6 squared is?
36.
36.
Okay. And then last example here, you have 8/27ths all to the 1/3 power. Remember, 1/3 power means the exact same thing as?
Root.
Yeah, cube root, third root of that. So what's cube root of 8?
2.
Cube root of 27?
3.
And carry on. So we're going to be using the exact same rules as we've had in the past. It's just a little bit different with the fractional amount. But as you can see, the properties work out rather cleanly. If it was a fraction you're not sure of simplifying on your own, please just use your calculator. It doesn't work for you. Okay? But that also means we're going to have a lot more going on. It's good times.
I really like your decorations. Should have been here during question day trying to find
Oh, it's going to be crazy later, but it's still kind of early. So in this case here, I have the same base, different exponents again. What do I have to do with my exponents?
Multiply.
multiply and add.
I mean, by multiplying you add. So.
What's 1 half plus 1/4?
3/4.
3/4. And just leave it as 5 to the 3/4. The general rule for these types of problems is, you know how we have exponent rules and then we have nth root rules?
Yeah.
If the problem starts out with the exponent, leave it in the exponent as you're finished. If the problem starts out as an nth root, leave it as an nth root as you finish. It's pretty straightforward when it goes to that. Here I've got division again. It's 7, but there's no what?
Why don't you multiply with 5?
Because that's not the rule. Remember when you had x squared times x to the third? That was the same thing as x times x times x times x times x. How many x's do you have? That's y. It's the same properties. Okay. Who wins in the Battle of War? 1 is smaller than 1/3?
The numerator, guys.
Numerator. So what's 1 minus 1/3?
2/3.
Okay. That one's a little bit weirder.
So we just focus on the exponents here. Pretty much.
No.
I have 12 to the 1/3 and 4 to the 1/3. Does that fraction, do those guys both have the exact same exponent? The exponents don't cancel themselves out. What happens here is that this is the reverse of one of the rules on your sheet. It's the reverse of the last one, I believe. This is the same thing as saying 12 over 4 to the 1/3 squared. What's 12 divided by 4? 3. And now you have power to power. What do you do with the exponents?
And
Multiply.
multiply.
What's 1/3 times 2? 2/3. You're using the same exact style properties. It just so happens that there's a fraction. Okay? Remember when you're working with n roots, same idea as we had in the past, where you could break them apart. For example, if you had something where it was the square root of 12, you guys knew that you could break that apart into simplifying that radical. What was the perfect square that went into 12? 4. So it's the same thing as saying square root of 4 to the square root of 3, so you got 2√3. What this is saying is that you can still break them apart with all the different n roots, but instead of looking for a perfect square, you might be looking for a perfect cube, you might be looking for a perfect fourth, fifth, so on. As you start to see some of these values and the numbers go through, it works out to be pretty clean. Also, you still have to be able to break apart your fractional amounts and the fraction roots again. You also don't want to have nth roots in your denominators. That's a big giant no-no. Just like we used to rationalize our denominators in the past, we're going to do the same thing with this stuff as well. If you do a couple of quick examples here, you're going to see it's the same exact process of what we've done over and over again. It's just got a little bit weirder of a twist because you have to worry about an nth root as opposed to just a regular square root. So let me show you a couple examples of something like this. Add the cube root of 4 times the cube root of 16. I can't do anything right off the bat here, can I? Or can I? Wait, what? Can I do anything?
Yeah.
Do I have the same nth root?
Yeah.
Okay, so what's 4 times 16?
64.
Okay, so that's the same thing here as the cube root of 64. What's the cube root of 64? 4. Okay. Again, I've got the same nth root. Doesn't matter what the stuff's underneath it, so I can multiply those two guys together. Then simplify it when I'm done. I have the fourth root of 162 over the fourth root of 2. I have the same root again, right? What can I do with the two numbers then?
Divide.
All right, what's half of 162?
81.
Good. So when you divide that out, you get the fourth root of 81, which is? Good. Yeah, there's not many of them. And you start getting, bless you, you start getting to so many of these things, they get so much bigger, they get so big so fast, so there's no reason to go crazy. I'd rather have you guys be able to recognize some of the more common ones than anything. Again, it leads us back into simplifying radicals. We all can simplify radicals when they're just boring square roots. We just talked about one like this. We broke it apart with a perfect square of 4, 3, so you got 2 root 3. What changes when you get into cube root, you're looking for the largest perfect cube. Now, remember, you're gonna have to start to know some of these off the top of your head. They start at 8, 27, 64, 125. Those are the first four perfect cubes after 1. Excuse me. So it was 1, 8, 27, 64, 125. Is there a perfect cube that goes into 54? What is it?
27.
27. So again, you're trying to see if you can split this apart into 2 of them. Bless you. What's the cube root of 27? 3. So your answer is 3, cube root 2. You all right? Now the weird stuff. Rationalizing. And this is usually where most people have more issues with it. So you have to kind of create something. In this problem here, I have the 5th root of 3/4. Can I side this up a little bit further?
Yes.
Do you agree that this is the same thing? Those are heavy. Now, in order to get rid of the radical in the denominator, the nth root in the denominator, we have to create a perfect nth root. So I have to find something that is a perfect 5th. Okay? How can I rewrite 4 in terms of an exponent?
1 to the 4.
No, that'd be 1.
So it would be 4 to the, on 4 to the 4.
No, 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 no.
4 to 4.
4 squared.
It's 2 squared, right?
2 squared.
On a good day.
What?
This is 2 squared, right?
I think it's 4.
Okay. If I want to make a perfect 5th, it means that something had to be raised to the 5th power, correct? How do I change the 2 squared into a 2 to the 5th? What do I have to multiply it by? 2 to the 3rd. What I'm doing here is I'm trying to create a perfect 5th root.
Where'd that 2 squared come from?
Right here, from the 4. I'm writing it in terms of a square. There's 2 ways you can go about this. This is one of the ways. The other one sometimes is a little bit messier. In this case here, I can write it as 2 squared. Yeah?
Could you multiply both sides by a quarter of
No. It doesn't work as clean.
Okay.
What happens here, because if you go, because it's the same thing, you want to eliminate the root. You need to get a perfect nth root. If you multiply by 4/5, it's the same thing. Because then you have 1/5, because this is 4 to the 1/5. Then you have 4/4. It's not square. What I'm doing here is that I want to change this by multiplying it by something to get it, the exponent, to a 5th. Okay? But if I multiply the bottom, I multiply the top. Because this becomes 2 to the 5th. I'm creating a perfect 5th. How many more 2's do I need to make it 2 to the 5th? I have 2 squared, I need 3 more. So I multiply by 2 cubed. Right. You try and create that. What is 2 cubed? 8. What's 3 times 8?
24.
So my numerator becomes the 5th root of 24. 5th root of jump to the 5th is jump. 5th root of 24 over 2. You're trying to create a perfect 5th within the denominator.
So we're kind of playing God.
Not really.
That's bad.
Another way you can look at it what are your perfect fifths? 2 to the 5th is how much? Why don't you use a calculator? Write something down. That might be helpful.
32.
It's 32, isn't it? What do you have to multiply a 4 by to turn it into a 32? Isn't that exactly what I did here? I created a perfect fifth root. I did the same thing. I just broke it to the exponents and used the rules. Because you might not know what your perfect fifths are. I mean, you can do 2s. You can do 3. I mean, you might be able to do a 3 in your head. It's tough. But 2s you can go up by. But if you break it down in terms of an exponent, remember, when you break down things to exponents, you're just adding them as you multiply across. So that's why it's a little bit cleaner to go that way. Right. That'll be the trickiest thing you guys will have to do with this stuff, is simplifying the radicals. You want to create that perfect fifth root, the perfect nth root, by using your exponent rules, multiplying by that power of 1, and going across. Adding, subtracting, you treat it exactly like you would as combining like terms. In order to be able to do that, you have to make sure you have the same value with the exponent, same rational exponent with the same term. You have to have the same nth root to be able to add or subtract as well. So in the first example up there, it's 7 times 6 to the 1/5 plus 2 times 6 to the 1/5. Are the things in the parentheses the same? If I called that just plain old boring x, what would 7x and 2x be? So this becomes 9 times 6 to the 1/5. And you go to the next problem.
I said 9.
The other one has a little bit of work. Yeah,
So you just leave it like that? You wouldn't
Done.
solve any
Nope.
question?
that's it. No, because there's no perfect, because that, remember that 1/5 means the fifth root of 6.
Right.
Nothing that's, there's no perfect fifth root.
Okay.
You're done. Don't have to worry about it. But in the other one, I have to do a little bit of work before I can get, you combine those. Is there a perfect cube root hiding in 16? What is it? 8, right? 8. So that's the same as the cube root of 8 times the cube root of 2 minus the cube root of 2. What's the cube root of 8? What's the or I want to say coefficient, but what's the number in front of the radical here that you don't see? What's 2 minus 1? There's your answer. You have to simplify before you add or subtract. You got to try to get the same nth root, or you have to work with the same rational exponent. Yeah.
So would you have to still do that if it was like something like right there, if you look for a perfect fifth root, like have that? Like when you do the 16, would it always be like that, or is it just?
It should always be like that. Otherwise, if there isn't one that you can combine, you just say it's done. It's simplified. You know what I mean? If it was like the third root of 20 minus the third root of 2, you can't combine those. You can't take out that perfect cube. Just like you did with this first. It's just an extra exponent. Okay. Same thing goes for when you have variables with this stuff. When you have the variables, you work the same way. Well, one thing I want you to remind you guys of, when you have variables and you're taking square roots, remember how we've always done a lot of the plus minus stuff here? What happens with these things is you read a lot of these instructions, it's going to state to you that you have all variables be positive. So in this instances, in this section, you don't really have to worry about any plus minus stuff, because it tells you so you don't have to worry about it. You don't have to worry about it. So what happens now is that there's some really nice shortcuts. We'll work with these one at a time. When I'm dealing with nth root stuff that has exponents and variables in there, you're going to find out real fast it's a really, really, really nice, easy way of working with this. Remember, when you have the cube root of 125y to the 6, you're basically taking the cube root of both of those terms. You're taking the nth root of whatever's underneath the radical symbol. So, cube root of 125. And now comes the interesting part. How many times does 3 go into 6?
2.
Are there any leftovers?
No.
There's your answer. What happens here is that you're using rules of exponents without writing it out. When you're dealing with nth root simplification, you're asking yourself each time when you have the variables, how many times does your nth root go into each of those variables? We use the same example with a different number. If I have the cube root of 125 y to the 8th, z to the 9th, we know the cube root of 125 was 5. 3 goes into 8. How many times? How many are left over? Okay, so that means 2 y's come out, 1 y, or 2 y's stay in. 3 goes into 9. How many times? Are there any leftovers? So 3 z's have to come out. What you're doing here with your nth root stuff is you're figuring out, you're just doing shortcut division. In essence, what you're doing here is you're simplifying a fractional exponent without writing it that way. Yeah.
So if there's any leftovers, they'll go inside.
Yeah, leftovers always stay underneath the radical.
All right.
All right. And as we do a couple of these, you're going to find out nth root stuff is a breeze when you write it out like that. Nth root is a breeze.
So you just end it right there.
You're done. Nothing else you can do. Oh, I forgot my little cube root up here.
Oh, you need that?
Yeah. Same idea with this. I have the 4th root of x to the 4th over y to the 8th. Remember, that means I'm taking the 4th root of both the numerator and of the denominator. Yeah, exactly. 4 goes into 4 how many times? Are there any leftovers? Nope. So 4 goes into 8 how many times? How many are left over? And that's it. Nth root stuff is very, very straightforward. Okay, it's very straightforward when you walk through it like that. When he deals with the exponents, that's where still some of you guys tend to struggle. You guys still have a tendency to struggle a little bit when you're dealing with the exponent rules. 9u squared b to the 10th, all to the half power. That means that each one of those guys is taken to the half power. Do you agree? What does half power mean? Square root. Good. So when I rewrite this in terms of the exponents, I get 9 to the half. When you have power to power, what do you do with the exponents? Do you add them or do you multiply them? All right, what's 2 times 1/2? 1. What's 10 times 1/2? What's 9 to the 1/2? 3. Remember, what you're doing is you're sending this to all 3 terms using the rules of exponents. And you're simplifying it that way. Okay? The exponent one should not frighten you. But remember, you'll probably have more like 2/3, 4/5, things like that when you have power to power, as opposed to having the weird end roots type stuff. Your end roots, you'll have, cube root, 4th root, things like that, but you won't have it raised to that extra value of them. And it's the big ones that you guys. So if I have 6y to the half all over 2x to the 1/3 z to the -5th. Whenever I do these big problem style, nasty looking things, I always do the same steps. I always start with my numbers first. After that, I make all of my exponents positive, and then I simplify. Okay? So if I start with this, what's 6 divided by 2? 3. X, y to the 1/2 are all positive, so I'm just keep them here. The 2's been taken care of. X to the 1/2 is positive, or 1/3, so it stays in the denominator. Where did the z to the -5 go? Up. Good. Now, I go variable by variable to simplify those last few steps. I only have to worry about one of them, x. What wins? X to the first or x to the 1/3? What's 1 minus 1/3? 2/3. Okay. So your final answer then is 3x to the 2/3, y to the 1/2, and z to the 5th. Again, if it starts with fractional, rational exponents, leave it in rational exponents. You don't need to go back and forth between that root stuff. Okay? Follow those steps, whether you're using rational exponents or integer exponents, and it should be clearer for you. Okay? I know you'll be able to do this one, so take a couple minutes, see if you can get both of them. I'm guessing the first one should be relatively straightforward. Can I take the 5th root of 5? I cannot, so it just stays in. 5 goes into 5 how many times? Are there any leftovers? And it comes out. 5 goes into 9 how many times?
Once.
How many left over? 5 goes into 13 how many times? How many left over? Nth root simplification, you should hopefully do very well at. It's pretty straightforward. Okay. What's up?
That's more simple than I imagine. I did it way over.
In the other one, you got to do a little bit more work. We cannot wind up with a radical within the denominator, so we have to figure out how do we create that y to the 7th into something that 3 goes into. So what you're asking yourself when you see something like that is, what's the next number after 7 that 3 goes into cleanly? 9. How do I turn a y to the 7th into a y to the 9th? Not add, but I have to multiply, yeah. So you would multiply the top and the bottom here by y squared. Because what you're creating then is the cube root of xy squared in the numerator and the cube root of y to the 9th in the denominator. Which is what in the denominator now? Y cubed. What you're doing is you're trying to create the next possible number that 3 goes into, or whatever that nth root would be. What's the next possible factor, multiple of the nth root, is what you're asking yourself in these. And that's how you rationalize, if you will, when you're multiplying these things out. You're just looking for the next possible clean value that it goes in.
Is that your answer?
Yeah, you're done. You can't go any further because you can't simplify the numerator at all because there's no perfect cubes that are in there. It's just x and y squared. Now, if it was like x to the 5th or something like that, you can continue to simplify, but in this case, we can't. Yes, sir.
For that last one, how is your answer like any simpler than what you started?
It's simpler because it's proper. It's proper because there's no nth root in the denominator. Just like when we had, the square root of 3 over the square root of 2, we didn't like that. We had to rationalize it. We wound up with root 6 over 2. It wasn't any cleaner looking, but it got rid of that in the denominator. Same thing when we had imaginary numbers in your denominator. You didn't like that. You had to multiply it up, get rid of it. There are just certain etiquette rules in math that are there. It's like starting with the farthest out fork as you're eating a nice dinner and you work your way in. What's that?
Miss Morris.
Oh, I don't know.
Foods teacher.
Oh,
Wonderful foods teacher.
I don't know. Again, adding, subtracting, simplifying expressions with adding and subtracting, you're looking to make sure that you have the same nth roots or the same exponent, rational exponents to be able to do that. Sometimes you might have to simplify something here or there to make it work. Sometimes you'll be pleasantly surprised. For example, 5 root y plus 6 root y. 11 root y. Okay? 2x to the 1/3 minus 7x to the 1/3. Good. Negative 5x to the 1/3. xy to the 1/3, excuse me. Okay? The last one is where you have to do some more work. Of course. You save the best for last. Remember, in order to add or subtract these things, it has to have the same nth root as you walk through it. So I have 3 cube root of 5x to the 5th minus x cube root of 40x squared. Which means I got to simplify both of those nth roots before I do anything to see if I can get that common nth root, if you will. So the first one, what can you simplify? What can we do?
X cubed.
Yeah. So what happens here is that I can't, 3 stays. I've got the cube root of 5. I can't do anything there. But 3 goes into 5 how many times? Once, and that's why you're saying pull out the x cubed, because the cube root of x cubed is x. And you have an x squared left. All right? 3 goes into 5 once, 2 left over. So now I have an nth root here. I try to simplify this again on this side. So if I have a 5x squared underneath my nth root, and I have a 40 on the other one, what should I try to divide the 40 by? 5. Because what happens is you get the cube root of 8 times the cube root of 5x squared. What's the cube root of 8? 2. So you wind up with minus 2x cube root just by working from some simplification like that. Okay. So do I have the same 3x and 2x, and I've got a cube root 5x squared? Can I combine those like terms now? What do you get for your final result? So 3x minus 2x is 6? X. Yeah, you get just x. I'm not exactly sure where you're going with that one, but all right. And that's your final result. Okay? It's the rationalizing of the nth roots that'll probably be the most difficult of all of this stuff, to be honest with you. Please work through those. I gave you odd numbers so you can check your work this time. Problems like that.
I'm sure that's being checked.